In this video, we're going to solve a few more circuits using node voltage method where these circuits contain a supernode. So in this circuit here, as you can see, this 2-volt source creates a supernode because neither side of it is ground. Now, in addition, what's different in this circuit that we haven't seen before is that there's a 10 ohm resistor that's in parallel with this voltage source that makes the supernode. So when you have a case like this, when there's a resistor in parallel with the supernode, that resistor is part of the supernode. So we treat this voltage source and this 10 ohm resistor for the purposes of writing a KCL equation as a single node. So we've got two unknown nodes, V1 and V2, but V1 and V2, they're part of the supernode. So we're only going to have to write one KCL equation for this problem. So KCL at the supernode is going to be 2 amps flowing in, and that's the only current I have flowing in to the supernode. And then I have I1 and I2 and 7 amps flowing out. Okay, then I write the currents through the resistors in terms of voltage using Ohm's law. So I1 is going to be V1 over 2, right? Since this is ground, it's V1 minus 0 over 2, so just V1 over 2. I2 is going to be V2 over 4, and then plus 7. Actually, let me point out one common error that students sometimes make when they're first learning about supernodes is that they'll do this correctly. They'll write the correct KCL equation because they treat the supernode as a single node when they write the KCL. But then a mistake they'll make is that when they write these currents in terms of voltage using Ohm's law, they'll treat the supernode as still a single node. So I've seen, students, instead of putting V1 and V2 here, they'll call the supernode, the voltage for the supernode, they'll call it like VSN, so they'll have VSN here and VSN here. But remember, you only treat the supernode as a single node to write the KCL. After that, when you write the currents in terms of voltage, you're treating it as two separate nodes again. So just something to keep in mind. Alright, so as you see, when we're done with our node voltage expression at the supernode, we need another equation. And we get that other equation just like what we've been doing before, is we look at this voltage source and it tells us that in this case V2, okay, the voltage on the higher end of the 2-volt source or V2, that voltage minus V1, the voltage on the lower end of that voltage source, has to equal the voltage source value of 2. Okay, so here's our two equations, two unknowns to solve for. And if you solve for those voltages, let's see, I got that V1 is a negative 7 1/3 volts, and that means V2 has to be 2 volts higher than that. So V2 is minus 5 1/3 volts. That's a 3 there. Okay, 5 1/3. Sorry about the sloppy 3s. Okay, so minus 7 1/3 volts and minus 5 1/3 volts. Those are our answers for our node voltages for that problem. Okay, one more problem and we'll be done with node voltage method and we can go on to other things here this quarter. Let's look at this circuit here. Here we have two supernodes. Okay, because see, we have two voltage sources where neither side is ground. So here's a 10-volt independent source that makes up a supernode, and here's a dependent voltage source. See, the diamond shape, remember, tells you it's a dependent source, and the polarity inside the diamond tells me it's a dependent voltage source, and that dependent voltage source has value 5I volts. So its value in volts depends on this current I, which is defined for us as the current through the 2 ohm resistor, going down through the 2 ohm resistor, so the higher end voltage is on that side. Now I defined these currents, I2 and I3, and also in this circuit there's a resistor that's in parallel with these supernodes here. And when you have a case like that, that resistor is also part of the supernode. So you see, we're going to treat this whole part of the circuit right here as a single node when we write the KCL equation. So let's go ahead and do that. Okay, KCL. Okay, so this is the KCL at the supernodes, right? Since we got more than one. Okay, so it's just going to be these three currents here. It's going to be I flowing out plus I2 flowing out plus I3 flowing out, and then we don't have any currents defined as flowing into the supernode, so it's just going to sum to 0. Now, before we write these currents in terms of voltage using Ohm's law, let me just state that, you know, if you did not include this 6 ohm resistor as part of the supernode, well, you would define a current flowing out one end of the supernode and a current flowing into the other end of the supernode that was going through the 6 ohm resistor. So even if you didn't include it, it would cancel out anyway, right? Because if I, you know, define a current, let's say I4 going through the 6 ohm resistor, well, it would be leaving one end of the supernode and entering the other. So on the KCL equation, you'd have I4 on both sides of the equal sign, so they just cancel out. So you end up with the same thing. Okay, but now let's go ahead and write each one of these currents in terms of voltage using Ohm's law. So I is just going to be V1 divided by 2. I2 is just going to be V2 divided by 4. And I3 is just going to be V3 divided by 3. And then that equals 0. So you see here we're done with our node voltage expression, but look, we're 2 equations short. Right, we've got 1 equation, 3 unknowns. So again, getting the additional equations comes from looking at the voltage sources and seeing how that affects our node voltages that it's connected to. Okay, because that gives us the relationship between the node voltages for the additional equations that we need to solve. So the 10 volt source, looking here, V1 minus V2 is 10 volts. Okay, so we get this equation by looking at the 10 volt independent source. Okay, and then the dependent voltage source, well, V3 is on the higher voltage end and V2 is on the lower, and this is the difference here. So looking at the dependent voltage source, we get this expression. We get V3 minus V2 equal to 5I. Okay, so now looking at our 3 equations here, well, look, now we've got 4 unknowns and 3 equations, right? Because that dependent voltage source introduced this new variable here as part of our node voltage expressions. So you see, I need to now write that current that the dependent source value depends on in terms of what we're solving for. And we're solving for node voltages. So that's when we look at, well, where is I defined? Well, I is defined right here. It's the current through this 2 ohm resistor. And I can write that current through the 2 ohm resistor in terms of a node voltage, namely V1, by using Ohm's law. So you see, that's what we need to do here, is just plug in I, which is V1 over 2, right? I mean, that's what we did over here, right? I is V1 over 2. So now here's our simultaneous equations to solve. Okay, 3 equations, 3 unknowns. And again, I'll just give you the answers here, and you should make sure that you can work through and get these. V1 comes out to a voltage of 3.043 volts. And V2, okay, for V2 I got negative 6.956 volts. And for V3 I get 0.656 Okay, so make sure you can work through the equations and check your answers against mine. You got to make sure that you can solve the equations, but then more importantly, also for added practice, you know, and hopefully you've been doing this for all these node voltage problems that we've been doing, is that once you obtain the answers to the equations you solve, you know, go back to the circuit and make sure you can find current, voltage, and power for all the elements.